All right, thank you everyone for coming to our talk about the Windows notification facility. So just to get started, I'd like to introduce my co-speaker, Gabrielle.
So, hey everybody, I'm Gabi, reverse engineer at Quarks Lab in France, and I'm focusing on the Windows internals and more specifically the kernel. I'm also belonging to the Black Hoodie organization crew, where we're trying to show newcomers ladies that reversing is fun. And that's pretty cool for me.
Thanks, Gabi. You know, it's very rare that it happens that you do research and you end up having a collision with someone, and instead of fighting over who's going to present and trying to get into all sorts of pestering, it's nice that we're in a community where two people who met at a conference doing similar research got to combine their research. So I'm very lucky to have Gabrielle here, who helped out a lot with some of the stuff you're going to see in this talk. For those of you who don't know me, my name is Alex Ionescu. I'm currently VP of EDR Strategy at CrowdStrike, and I'm a passionate Windows internals researcher that has been doing this for way too long now. Publisher of the Windows Internals series, and often speaker at various conferences about low-level things in Windows that no one knows about that are interesting to misuse, abuse, or otherwise play around with. And hopefully you'll see some examples of that in this WNF talk. So first of all, we'll start by talking a little about what WNF is, why it exists, why it was built, how it works, some of the APIs to use WNF, and then Gabrielle will go over some of the data structures for those of you who are doing forensics or kind of want to understand how it works behind the scenes. And we'll also talk about some tools that we've built together, some Winbag extensions, some Python scripts, some C scripts that we'll be releasing so that you can also fuzz, manipulate, and play around in the WNF area. Then I'll take you some of the interesting attack surfaces that WNF provides. Like most kernel functionality, it's not inherently bad. It's just the way people use it and what can happen when you misuse it and kind of break the assumptions. When things are undocumented, there's often a lot less fuzzing and security testing that goes on within the vendor because they figure, hey, it's undocumented. Until someone talks about it, we're okay. Phew. I'll also talk about interesting use cases of WNF that are probably not intended, things like using it as a covert side channel, as well as using some of the notifications that it provides for rootkit-like, implant-like behavior without doing some of the hard work someone in that space normally has to do. It is a kernel-level facility, and so it allows you to get very fine-grained information about the system, and you can see some examples that you often can't do in kernel mode at all, or that's very, very complex. And again, piggybacking on the system or living off the land is something that's very popular these days in security research. And I'll also talk about a few examples on how WNF can be used to manipulate system state. Instead of global variables, more and more state is now stored in WNF data. And again, you can manipulate a system in interesting ways, either as an administrator or not. And then we'll wrap up with some future research ideas that we've come up with. So let's talk about, first of all, what is WNF? So the Windows Notification Facility. This is a new kernel component that was added in Windows 8, and it's essentially a pub/sub model, publisher subscriber. And so you have one side that's basically publishing data, publishing notifications, and you have one or more subscribers or consumers on the other side that are consuming that data. Now, the way WNF was built is actually very nice because it fixes some of the design limitations that Windows had before. And I'll give you an example of something you couldn't do before WNF. Now, what's really cool about it is that it's completely blind. In many pub/sub models, the publisher has to come first. You can't subscribe for something that hasn't been published yet. And if you're a publisher and you're publishing something before the subscribers, then subscribers might miss the data. And so there's a lot of synchronization and a lot of classical pub/sub models around who publishes first, who subscribes, and so on and so forth. With WNF, it's kind of a blind system, is registrationless, and so the publisher and the consumer or subscriber don't really need to know about each other's or who loads first before the other. So it kind of supports out-of-order behavior. On top of this, it has lots of cool features like persistent data versus volatile data. It has a change stamp, so you can see if someone's modified the data in between you last reading it. It supports Windows security descriptors, so it's kind of got all the features you'd expect out of a mature Windows kernel functionality. And a good example for why you need something like WNF is on Windows. The example when you write a Windows driver that loads at boot and you want to write to the disk. Now, the disk, when Windows boots up, is initially mounted read-only. This happens in every major OS in the world, and even Linux and Mac OS boot a disk read-only. Then at some point, they run a utility like fsck or autocheck in Windows' case, which makes sure the disk is safe for writing, fixes any bad sectors, and then remounts the drive as read-write. At that point, a driver knows that it's safe to write to the disk now because autocheck executed. Now, to do this, autocheck signals an event that's named. But who creates that event? Because if autocheck creates the event, then any drivers which load before autocheck don't have an event to wait on because the thing that tells you autocheck ran doesn't exist yet. If the drivers are supposed to create the event first, then which driver becomes the first one to wait on the event becomes the one to create the event. And again, you end up in these weird ordering problems, which were fixed in this particular case by having the kernel very early at boot being the one that creates the autocheck event. That way, autocheck always knows it can signal it, and drivers always know it's already there. Someone took care of it for them. But this is for this one specific use case, right? I'm sure some of your programmers, you've had similar issues where there's some event out there that one side needs to signal, another side needs to wait on. How do you wait on something before it exists? Right, WNF solves that, because with WNF, I can subscribe to that event and block, even if it doesn't exist yet. And when the event actually gets created, then I'll actually wake up once it gets published too. So that's kind of one of the top use cases, is blind registrationless subscription model. Now in the WNF world, what you have aren't events, they're WNF state names. These are basically 64-bit IDs, they're just numbers. But there's a trick to it. These numbers actually encode a data structure inside of them. They're not just random numbers, they actually are bits that represent a version, a lifetime, a scope, a permanent flag, and then a unique sequence number. The trick is you take a WNF state name, you take the 64-bit number, you XOR it with this magic key here, which, who knows what it really means. I don't know if it's some person's name, an ASCII or whatnot, but you XOR it with this key, and then you get this data structure out of it with these different bits that are gonna mean different things. So they're not just GUIDs, they actually have meaning associated with them. So the first meaning is the lifetime. WNF state names have lifetime, and there's three main lifetimes that are used: well-known names, permanent names, and persistent names. And then there's a fourth type of lifetime, which is a temporary name. Now, well-known names are actually in the registry, and they're published and basically created when the Windows installation media is created. So these are in a header file at Microsoft, and they basically get added in the registry. Permanent names are names that can be registered after the fact. They're also stored in the registry. So once a permanent name gets registered, it persists. Its data may or may not persist. There's a flag that specifies should the last data that was associated with this state name be persisted or not. And then gets a little bit confusing. There are persistent names, which go in a registry key called volatile notifications. So persistent names are persistent with regards to the process that registered them, but they're not permanent across reboots. So if I'm a process and I register a persistent name and I exit, the data and the name of that WNF state name persists until I reboot, and then it's gone. A temporary name, if I create it and I exit, it's got no registry backing associated with it. Once the process exits, the temporary name is gone. So temporary names are bound to the lifetime of the process. Persistent names are bound to the lifetime of the system. Permanent names are in the registry forever. And then well-known names are in the registry, but you can't register them. They're kind of pre-registered well-known names that the system is going to use. And this kind of follows a similar model as objects, where unless you're an administrator or you have the create global name privilege, you can't create permanent or persistent names. You can only create temporary names unless you're an admin or above, and then obviously you can do that. The second piece of a state name is its scope. And the scope determines basically the initial security boundary and visibility boundary around a WNF state. So a WNF state name can either be global, or it can be unique to a session, or it can be unique to a user, or it can be unique to a process. So you can say only this process and its threads know about these state names, or only the user, only Alex's processes can touch the state name, or only whoever's logged in session 1 can touch a state name, or anything across the system can do this. So there's different scoping that you can associate, and lifetime and scope obviously go hand in hand together. For example, you couldn't create a permanent name that is process scoped. because that wouldn't make sense. Once your process is gone, the process scope is gone. Why are you persisting this name that no one will ever be able to open again, because no one will ever be that process again? So there are some rules, obviously some scopes don't make sense for certain lifetimes and vice versa. And then the last piece is the sequence number. Because since these names are just bits, well, some of the bits are the scope, some of the bits are the lifetime. One bit says if this is persistent data or not. How do you then actually make the name be unique? So there's a 51-bit sequence number. Now for well-known names, the first 32 bits are basically characters, kind of like a pool tag or a heap tag. It's 4 ASCII letters that kind of define the family, the tag that really is associated with this name, and you'll see some examples soon. The remainder of the bits, the last 21 bits, are then used as a number within that family. So this is the, let's say, I don't know, let's come up with a tag called BKHT event 1, right? So BKHT, that's your tag, that's your first 32 bits, then 1 is the first black hat event, and then 2, 3, 4, 5, and so on and so forth. That's for well-known names. For the other names that want you to register at runtime, the persistent names, the permanent names, that sequence number is a monotonically increasing number. So the first ever permanent state name that was ever created, its sequence number was 1, and then 2, and then 3, and then 4. And the last used sequence number gets written in the registry, so every permanent name until you reformat your drive will always be increasing. Then the persistent and temporary names, which disappear once you reboot the machine, those have their own monotonically increasing sequence number that obviously gets reset to 0 once you reboot the machine. So somewhere in a kernel variable, we basically remember this was the last, non-permanent sequence number, and we'll just keep incrementing that. So here's an example of a state name, WNF boot dirty shutdown. Like that's its friendly name. That's kind of what you can see in the symbols. What it looks like if you open this up in IDA is 15890, a bunch of hex numbers. You XOR those hex numbers with that magic key, and then you get something that still looks like magic hex, but it's a little bit more readable now, right? And some of you can probably recognize, okay, that looks like ASCII. Okay, there's some meaning to this. And if we follow the data structure from earlier, well, this 1 basically tells us this is version 1. This 0 over here tells us that this is a well-known system scoped name. And then obviously these ASCII characters represent the word boot. And then the 1 over here, this isn't 1 shifted, obviously, so it looks like an 8, means that it's the first event part of the boot family. So WNF boot dirty shutdown is that number, but that's internally like how it's represented by the WNF system. So to register names that are not well-known names, there's a nice little API, a system call, create WNF state name. You pass in the lifetime, the scope, whether or not data should be persisted, the size, a secure descriptor. It goes in the registry, or if it's temporary, it doesn't, and then it creates this name for you. If you want to get rid of it at some point, you call ZW delete WNF state name, and then this will then get rid of it. Then if you want to add data, if you want to send a notification, there is a update WNF state data in which you pass in the state name, a buffer, a size, and then something called a change stamp. And the change stamp basically lets you say, well, look, every time I publish data, there's a unique timestamp that's basically a monotonically increasing number that says, data entry 37 was written to. And then it's 38, and then 39, and so on and so forth. You can say, look, the last time I published data, the timestamp was 40. And so now I believe I'm publishing timestamp 41. So I can enforce that basically says, if someone else has already published something, then ignore what I'm saying. So you can put a matching change stamp that basically says, I expect the data to currently be 40. If it's 41 or later, that means someone already did an update. Or you can say, I don't care if someone updated data, just go ahead and publish it. So that's what that change stamp concept is about. It's kind of like a sequence number that you can use to see if anyone's made a change or not. If you want to delete data, you can call ZW delete WNF state data, and then this gets rid of it. To read WNF data, there is a ZW query WNF state data, which gives you the data, the buffer size, and the current change stamp of the data that you just read. Now, the real power of WNF, though, is that both for consuming data and querying data, the name doesn't yet have to be registered. Unless it's a temporary name, which wouldn't make sense. If it's a persistent, permanent, or well-known name, even if it's not been registered by anyone yet, you can still publish data to it. the kernel will basically allocate a buffer where it says, okay, for this name that I don't know about yet, here's the data that's going to be associated with it. So when the consumer, when the publisher comes in and says, now this name exists, well, then I can just associate the data that was already kind of associated with the name, even though the name wasn't even published yet. And vice versa, I can ask for data, even though the publisher may not have published it, because I could have it from a previous reboot, for example. So this kind of disassociates the data associated with a state without the state needing to really exist yet, with the exception of temporary names. Because obviously temporary names are completely based on a sequence number that gets updated every time you reboot. If I publish data to a temporary name before the temporary name gets registered, I don't know how to associate those two things, right? Because there's no kind of static information associated with it. And so when you query or when you publish, if the name doesn't exist, there'll be an instance created anyway. And then when Gabriel talks about the data structures, you'll see that name instance data structure. So far we've seen that you can create a state name, delete it, and then publish or read data from it. But what if the data doesn't exist yet? Well, then the last thing you can do is set up a notification. And so there's a bunch of system calls that allow you to be notified whenever data gets published to a state name. The way this works is you call an API, ZW set WNF process notification event, to first associate an event with your process. Then you call a different API, subscribe state change, that lets you specify that you want to be notified when certain things happen to the state, either when data gets published or when the state gets destroyed, or you can even register to know when someone has subscribed to the event. It's basically called a meta notification. It tells you when anyone else has also subscribed for the thing you're also subscribing for. That's something you can do. Then your event will get signaled. So you wait on your event handle. Every time it gets signaled, you call get completion WNF state subscription. This gives you a delivery descriptor that basically shows you the last update that was just pushed. What data, what size, what is the change stamp that caused you to wake up. And so initially I had a POC that used these system calls to basically be notified, and I was trying to hit various keystrokes, launch various apps, and see what WNF IDs were being lighted up when I was doing things. Eventually, when I shared the code with Gabrielle, she found out that it wasn't working on some of her systems, that my code was basically failing. And the reason for that is only a single event can be associated with the process. So as soon as someone wants to be notified about one WNF state, no one else can be notified about any other states because only one event can be associated with one process. So like, well, how the heck does this work then if there's multiple WNF consumers? And it turns out that in NTDLL, there's a higher level API. You're not supposed to directly call the system calls. Those are actually meant for NTDLL itself, which does this as process startup, registers its own event, and then everyone else is basically getting multiplexed by NTDLL. And so there's an API called RTL subscribe WNF state change notification, where you're asking NTDLL on your behalf to subscribe for this. It uses its event, and every time its event gets signaled, it goes over the list of all the current subscribers in the process, figures out who owns this particular event, and then notifies that subscriber by issuing a callback. So you're supposed to rely on this, not on basically calling syscalls yourself if you want the notifications to work. And this will have some interesting use cases when we talk about forensics and some attack surfaces. So that callback basically gives you the name, the stamp, the buffer, and the buffer size. And this is how inside of your process you can know that there's data that's been published for one of these WNF state IDs that you've registered for. Now, there also is a kernel mode API. So in kernel mode, there also is an EX subscribe WNF state change, which lets you do the same thing as the kernel driver. And then the driver gets a callback, and the driver calls EX query WNF state data to read the information that's there. So both drivers can publish and consume WNF data. Both drivers in user space applications can get notifications for WNF as well. So you can communicate across process boundaries, across session boundaries, across user kernel boundaries. And obviously it's very interesting when you have an IPC mechanism that's this rich, that crosses these many boundaries, and kind of hence the interest of looking at it in more detail, because no one's really talked about the WNF in the past. So that's kind of the basics of how it works. And we're going to publish all these slides, obviously, so you're not have to memorize how those APIs work. And what's good is that they accidentally all leaked them in an old Windows header file. So they're available, if you know where to look, but you'll have the slides as well. So next up, I'll pass it off to Gabi to talk about some of the data structures that are involved in the internals of keeping track of all this data.
Thanks, Alex. So now you have basically a good understanding about the WNF mechanism. So let's dive into the structures. So a WNF event is identified in memory as a name instance. These structures basically hold all the information related to the event. For example, you can find the state name, the scope in which the event occurs, the security descriptor, and so on. You may notice that the first field of these structures is tiny structures named the WNF context header. In fact, these structures give information about the type of the structures and the size. And in fact, most of the WNF structures has these headers. So it's kind of convenient when you're in memory and you want to identify something you don't know because you just have the header. Another thing that is interesting is that in the instance name, you have a pointer to the data that will be sent to the subscribers. This data starts with a WNF state data structures that gives information about the size of the data and, for example, the number of times it has been updated. As Alex told you, an event occurs in a specific scope. So the scopes are represented as scope instances. This scope instances gives all of the stuff needed to identify the scope. And they also got a list of name instances that are available on this scope. Well, when I say a list, it's not a list, it's more like a binary tree that enables a quick lookup. And all these scope instances are stored in a list tree, and the scope map enables to keep track of all of that. You can find the scope map in the server silo globals, and basically, it's bound to one silo, bound to the silo. Okay, so when a consumer wants to subscribe an event, it creates a WNF subscription. This subscription basically stores all the information needed to, for the WNF to notify the consumer. It also stores the state of the subscription and the method, the way, the delivery option, in fact. Okay, last structures in kernels I will present is the process context. In fact, there's structures that keep track of all the different objects related to a process. And you can find it in the eProcess object. So, you may notice that the last field is actually the notification event. So that means, you can just have one event, as Alex told you. So how the WNF managed to circumvent the problem of having only one single per process notification? Well, when you are using high-level APIs, you're actually dealing with a set of user-long structures. This enables multiplexing of subscriptions. And to keep track of all these different objects, you have the subscription table. And basically, if you have a sub-consumer that wants to subscribe an event, you will create a WNF name subscription. This structure is unique for a state name in the process context. And then you will also have a WNF user subscription to have the information about the notification mechanism for the sub-consumer. So this way, you can have one WNF name subscription and several WNF user subscription. So that's how the issue is managed. And I think that's quite cool. Okay, so I finished for the structures, and I will present some tools. Oh, well, we are presenting some tools. So as you can see, there's a lot of structures, and it's quite a hassle to keep track of all of them, to intensify them when you're debugging. Hopefully, you have a native WinDebug command, which is called bind Wnf, that provide and display relevant information about the structures. The thing is, it doesn't work out of the box because it relies on the symbols, and obviously we don't have any symbols. But you can fix it by adding the structure definition to your PDBs. And with that, the WNF command is working. The problem is, well, even if you manage to fix it, you will still have a bunch of errors popping out. I think, well, it feels like the command wasn't really finished, and it's not totally polished. It's quite strange. Basically, I had to patch the DLL for displaying some of the features, so it's quite strange. So for all these reasons, I decided to create my own extension. It's nothing fancy. It basically do all the things that the command line or the command does already. But it doesn't rely on your PDB symbols, so it should work out of the box and smoothly. Nothing related. I created a tiny Python modules thanks to your script. See? For enabling communication via WNF. Basically, with this module, you can read and write to an existing name instance, or even create a new temporary state name for creating some kind of server side. And with the client side, you can just communicate. And it's really easy to use. I show you an example where I just created a server and a client, and they can communicate. And yeah, that's fun.
Great, thanks, Ariel.
No problem.
And apparently, this is what goes for not very fancy. It's just she just put 50 commands in there that are super awesome, but it's nothing fancy. I created something that's really not fancy, which is a little C tool. I don't do Python because I suck. So this C tool, WNF dump, and basically what it lets you do is just dump all the state names, and I'll do a little demo. It lets you brute force state names as well. I'll show you how actually you can brute force the names that are not well known. It lets you read a state name, write into a state name, or register for a notification on a state name. So very, very simple tool. Here's me running it with -d, saying just dump all the states, and it just starts dumping all of the WNF IDs. Some of these you're going to see look pretty interesting, and we're going to talk about that very soon. Kind of tells you if they're system-wide or per process, if you have write access or not, if there's any current subscribers to it, if you have sorry, this is the scope, read write, read only. And then it gives you kind of the current change stamp. So that kind of tells you how many times this has been updated. Obviously, if it's 0, it means no one's ever written into this. And then basically how much data is currently in this event. So once you have the tool to play around with, obviously it'll probably make a lot more sense. But it's kind of something I used initially to kind of figure out, what are different WNF IDs out there that we can start looking at and playing around with. And again, many of these seemed very interesting just from kind of looking at them from the beginning, and I can start dumping them, looking at the security descriptors, and so on and so forth. So hopefully with these tools and the extensions, once we release them, you can do your own research and find out more, because we've literally only scratched the surface of everything that's out there. And so let's talk about kind of what are some of the interesting areas where you can start poking at WNF. The first, and some of the kind of findings that I had. Because some of you know me, I don't do fuzzers, not because I look down on them or anything. I'm just not a fuzzer person. I like finding design logic issues. But accidentally, as I was writing WNF dump, I kind of turned it into a fuzzer because one of the ways I wanted to see if I have access to modify a state name is instead of getting its security descriptor, I just tried writing into it. And I said, look, if I just write 0 bytes, what could go wrong, right? It's actually pretty naive because if you write 0 bytes, you're overriding anyone that had ever written anything in there whose data hadn't been consumed yet. So when the consumer comes along, they get my 0 byte payload instead of the real payload. Also, every write changes the chain stamp. So anyone that was trying to write to it legitimately with enforced change stamps saw some other thing already modify the data. So what ended up happening after I wrote 0 into every single WNF ID on my system is Explorer just disappeared. I could never relaunch it. I rebooted the machine, and I was greeted by a black screen. I'm like, that's not good. And I had to fix it by basically going on a different machine's registry, exporting all the WNF ID data back. And I was like, right, data is persistent. So I probably wrote a bunch of zeros in a persistent WNF state ID that something in the system relies on. But the interesting thing is I had run WNF dump as a standard user. So like, oh, a standard user can nuke a box. Cool, I think I should do more research on this. Another thing that I did is I eventually dumped every single byte that was there in every single WNF ID, both as admin, both as system, both as standard user. And as standard user, when I started reading some of the data that's there, I started seeing things like, wireless network names and things like pointers. Data that's privileged across process boundaries, user boundaries. There were some globally scoped, world accessible WNF state names whose data really shouldn't be exposed that way. I submitted these to MSRC last week because I was reminded that actually these types of issues do matter. Information disclosures are considered security boundaries, and it's hard to keep track of all that. So that's one reason why I can't share the tools or I won't name names, because if you run the tools, you will literally see that in like the first 3 seconds. So please don't do that. Wait for them to fix it. And so that's why these tools will come out once these issues are fixed, because we don't want to make it easy for people to just rediscover the same bugs. Another thing that I've noticed is when I accidentally wrote some data in one of the WNF IDs, I wasn't able to launch any modern apps anymore. So Calc is modern nowadays. Regedit worked fine, Notepad worked, but Calculator, the new one in Windows 10, or any other Metro modern tile app wasn't launching anymore because it had accidentally corrupted one of the state names. Rebooted and it worked again. Right, so I wasn't trying to fuzz and find these types of issues, but just kind of while accidentally writing into the wrong thing, these things are happening. The last one is when I run my tools as admin. So again, I had to be admin, so it's probably not an issue. But as admin, when I started writing garbage over the WNF world, I started getting service hosts to crash with null pointer dereferences. So probably not exploitable. Had to be admin anyway. Who cares about an admin to service null pointer? But it kind of showed me, what? If someone is actually competent in the art of writing fuzzers and creating polymorphic data and doing all the things that good fuzzers are supposed to do, and then logging what write caused what crash, I'm sure you could find something, right? I mean, if like me stumbling around, I got some things to happen, someone more competent can probably do a lot better there. So how do you kind of discover these names? So the first approach is to basically go for the well-known permanent persistence names. They're in the registry. So if you just enumerate the registry keys that are on an earlier slide that are also in the kernel, you can basically get all the state names. And the registry data that's there is the state data that's there right now, plus a security descriptor. So you get a security descriptor and the data that's there, and that's what my tool does. It basically parses that and shows it to you in a nice format. But temporary names, they're only known to the kernel. They're not in the registry. So I also wanted to fuzz or to play around with temporary names. I'm like, well, how do I get those without having a kernel extension? Well, if you think about a temporary name or a volatile name, again, it's a state name like any other. So it's got a version, and the version is always 1. It's got a lifetime, and the lifetime is temporary. It's got a permanent flag, which by definition is 0 because the temporary name can't have permanent data. And the scope is one of the 4 possible scopes, right? Machine scope, or process scope, or user scope. So the only part that's left to guess is the sequence number, and the sequence number is 51 bits. Well, how are you going to brute force 51 bits? You don't have to, because remember, the sequence number is a monotonically increasing number that starts at 0. So for permanent names, those are in the registry. But for temporary names, remember that it gets reset. So once you reboot the machine, how many state names can there possibly be? 20,000, 50,000, a million? Let's say a million. So I just basically loop from 0 to a million, try all the sequence numbers, and it turns out there's an API, query WNF state name information with WInfo state name exists. And this tells you if the state name exists or not. Now, if the state name doesn't exist, it returns false. If the state name exists and you're allowed to know that it exists, it returns exists. And if the state name exists and you're not allowed to know that it exists, it returns access denied. So you know it exists, right? So very easy to basically brute force what the names are, even though you might not be able to access them, at least you know they're there, so you can start messing with them. Now, the last problem is the security descriptors. How can you know what access you have to a state name? Again, with the kernel, I could just dump the ESD and see it, but from user space, the security descriptor isn't anywhere there. So I said, okay, well, if I can try reading from it, then I know it'll work, right? So let's try doing a read. Okay, the read doesn't work. I know I don't have read access. How can I tell if I have write access? Well, again, you can do this stupid thing I was doing initially, which is write nothing. But by writing nothing, you're destroying what's there. But remember that when you write, you can enforce the current change stamp. And what I thought is, what if I make the current change stamp be FFFFFFFFFFF? Well, if you have write access, you're going to get back status invalid change stamp, which basically tells you it's not an FFFFFFF right now. No write's going to happen, so you didn't corrupt anything. If you don't have access, you're going to get access denied, and it's still not going to change anything. So if I get access denied, I know I don't have write access. If I get invalid change stamp, I know I have write access, but thankfully I didn't modify the data. The only way this can break is if there is a legitimate event out there whose change stamp really is FFFFFFF. Yes, by writing into it, I will now make it overflow into 0 and potentially break something. But that would mean there's been 4 billion writes in a temporary state name, which should never happen. So that's kind of the approach I took when creating WNF temp. Now, what are some things you can do with WNF other than trying to, once you know what these names are? Well, one of the things you can use WNF for is basically a covert side channel. Right, let's say you want to communicate across process boundaries. There's lots of Windows API that lets you do that. But what's cool about WNF is you get these well-known WNF names that already exist that you don't have to register. So there's no Windows API that any EDR vendor can hook that tells you someone is using a well-known name, because the well-known name is already there. And so you can publish and read from a well-known name, and the only thing that anyone's ever going to see is that you did a system call. But in Windows, there's no way to hook system calls officially, right? And so reading and writing into WNF names doesn't reveal anything that vendors know about unless they know the registry keys where the data is being stored. So with well-known names, you can basically store data and read the data later by relying on parts of the registry that most people don't know what's in there. And without these actually being registry reads or writes, right? Because if you're an anti-malware vendor, who's doing the registry write? It's the kernel's WNF subsystem. Who's doing the registry read? It's the kernel's WNF subsystem. So by using state names that are defined but not used by anyone, you can kind of, by piggybacking on the registry, achieve a side channel that most people don't know what to look for. The other option is to actually create your own names. Now, if you create your own temporary names, this completely avoids the registry, right? So these are now going to be names and data that only exist in kernel mode memory, where most people don't know where to look, with the caveat that you do have to register by now calling ZW create register name. But as you're going to see, there's no ETW event, there's no kernel notification, there's no event log, there's no auditing of any kind when someone registers a temporary name. So unless you literally hook that API, which you all know you're not supposed to be hooking Windows APIs, it's a completely invisible way to basically exchange data between processes. And there are many other such ways, but this is one that no one's kind of named and put a logo on it yet. About atom bombing, now you can call WNF bombing or something like that. So that's kind of one interesting thing here. And so from an EDR anti-malware perspective, if WNF permanent or persistent names are used, you'll kind of see registry reads and writes if you know about those values. They'll come from the kernel. Behind the scenes, there's some process that's doing that. If they're temporary names, there's nothing you can really do to see that people are using WNF. Although there are ETW events. There actually is an ETW event for subscribe and unsubscribe, for callback and for publish. But only for user mode callers, and only if they're using the RTL APIs. So if you're in kernel mode and you're using WNF, no ETW trace is generated. If you're in user space and you're doing the system calls directly, no ETW trace is being generated at all. So it's a very invisible kind of IPC mechanism, which makes it interesting for me. Now, the other thing that's interesting is, what are some names that reveal information about the system that really perhaps shouldn't be revealed, right? And there's like 4,000 well-known names, so we're just going to go over a few of them. But for example, there's a WNF ID called WNF Wi-Fi connection status. This tells you the machine is connected to the Wi-Fi network and the current signal strength. And if you register a notification on this, even from kernel mode, for example, you'll get this data. Right now, if some of you are kernel programmers, you know the official way of doing this is like an NDIS lightweight filter and like sending OIDs. Now, all you do is one API and you get notified every time the wireless network goes up and down. There's one for Bluetooth. In fact, there's even one called tethering state. So every time there's tethering enabled or disabled, you get a notification. There's one called power source, which tells you if the machine is currently on AC adapter or living off the battery. If it's living off the battery, you can get the battery level from another WNF ID. There are cell phone WNF IDs on this thing called a Windows Phone, which here you can buy in some archaeological stores, which had information like the network you're connected to, LTE band that you're connected to. You know, if one day there's Windows Phones again, you know, those would be useful. There's one where you can infer user behaviors. For example, there's audio capture, audio render. This will give you a notification anytime someone plays any sound and or anytime someone captures any sound. So anytime I use Cortana, the capture WNF ID gets notified. TKBN touch event registers a notification every single time I touch my touchscreen, press the mouse or press a key, boom, that gets notified. In fact, if you want to do user detection, Windows has already its own built-in user presence detector, and it will notify SCB user present or SCB user present changed when the user leaves or approaches the machine based on the machine learning heuristics that Windows already has. So these are all things you could already do, but now you have a simple way of just registering for an ID that tells you when these things happen. There's also things that there's already APIs for. Like there is an API to get notified when a process gets started. But everyone knows about PS register create process notification. But did you know that there's a WNF shell desktop application started, WNF shell application started and terminated, that if you listen for these events, you will get the name and or the package name and the path of every single process creation and destruction, as long as it's down through shell execute. So sure, you won't get like non-shell based launches, but it's a nice way to get most interactive launch applications without calling any other API. You know, one of my favorite ones is WNF Edge Last Navigated Host, which basically, you know, I'll just do like a live demo, hoping the demo gods are with me. WNF dump -n, WNF Edge Last Navigated Host. All right, let's see if that works. Cross fingers, open Edge. Probably not going to work. Let's see. I know google.com. I'm not connected, so who knows? Oh, there we go. MBLR which is probably the Mandalay-based Wi-Fi network. So you know, now I can get every URL that's ever typed or clicked into Edge without any DLL injection or anything like that, including from kernel mode. Right? Another one is shell lock screen active. It tells you every time the lock screen is active, right? And there are thousands of these, right? So I'm sure you can find something interesting if you go over that list. There's also WNF IDs that let you change state. Like there's one called FSRTL op-lock break, where you write a bunch of PIDs, and there's a service in user space that terminates those PIDs for you. So you just write like 8, and it just kills PID number 8. Now you do have to be system. So this one is not something that, like, you know, app container can write in here. You have to be system. If you're system, you can already terminate a process, right? But you terminate a process going through mechanisms that most CDR tools know how to look at. Who the heck knows that if you write 8 in there, it ends up killing process 8? You know, there's other things like WNF cert flush cache trigger, which flushes the certificate cache, or boot memory partitions restore, which restores memory allocations. So there's WNF IDs that by signaling them, you get the system to do certain things. They almost behave like APIs, where you put some parameters, you signal the event, and then some service does some action on behalf of that. And you know, there's really lots of examples people will find. And so, if you want to kind of find things to have fun with, one of the things you can do is basically dump the WNF process context. And instead of a WNF process context, you're going to see all the active subscriptions. Now, if you look at a system process, all of its subscriptions are basically subscriptions owned by kernel mode drivers. And so you're going to see what are all the kernel mode callbacks that will get notified based on what WNF ID. And that kind of gives, this driver is my attack surface right here. And then the callback's obviously going to get a payload. And the question is, if I statically analyze the driver, what does it do with its payload? Is it actually correctly handling the data that comes in there? Now, in some cases, you're going to find an aggregator driver. There's a driver called the event aggregator, ea.sys, and it aggregates WNF IDs and it has its own sub callbacks. So there's drivers that rely on ca.sys, which then registers its own callback, kind of like in user space, you have NTDLL acting as an aggregator as well. In user space, there's an RTLP WNF process subscriptions table, and this table has a linked list of all the active subscriptions, as Gabriel talked about. For each subscription, all the callbacks that are associated with it, and given a process, you can see what are all the user mode functions inside of every DLL, inside of every function, and what name are they basically listening on. So that kind of gives you a good mapping of, here are all the code paths that I can hit by modifying or writing into certain WNF state names, and let me statically analyze the code, right? So you can either fuss things and just write garbage, or look into what the callbacks are and seeing what they're going to be doing. And so once you know that, you can basically signal arbitrary subscribers to see, what's the impact of the system once I do this. Are there fun things that I can do? One of the things I actually wanted to talk about is how you can play with Windows Insider features. Because all of the Windows Insider Preview A/B testing that Microsoft does, where they enable dark mode for half of you but not the other half, and they see if one half is jealous of the other half for either good reasons or bad reasons, is they actually encode thousands of A/B testing features as WNF payload inside of WNF ID. And as I was figuring this out, Rafael Rivera, a really great, Windows MVP and internals kind of person, he ended up figuring this out as well. And he actually created a tool on GitHub called Mock2, where it actually uses WNF underneath the scenes to modify which Windows Insider Preview features are activated on your machine. So even though you didn't get selected to try this cool new dark mode feature, with this you can kind of force it on. Or if you're like, yuck, dark mode, and you just want to force it off, you can do that. So that's kind of, one of the many things that rely on top of WNF. And if you go over and you look at what are some of the interesting insider settings you can enable, one of them is Windows Application Guard container for Office. Oh, cool, Office under Application Guard. I didn't know that was going to happen. The Andromeda store. Oh, so there is going to be a device called Andromeda. The CNN anti-spoofing data collection. Not going to get into that. Deep Inferno. I don't know what that does. Dev mode internal, right? So you can kind of see, new features that they're testing internally, and with WNF you can enable those on, like HVCI everywhere, or virtual machine chipset load firmware from file. So interesting things show up there, in the world of things that rely behind WNF. So if you're interested in some of the insider stuff here, definitely check out Mock2 by Rafael Rivera on GitHub. He uses WNF to kind of mess around with these things, and there's lots of other things you can mess around with as well. Another thing you can do with WNF that's kind of not by design is code injection, right? Lots of people love to migrate code from one place to another, and the way they normally do that is by either calling write process memory, or using file mappings, or using Atom objects, or Windows messages, or GUI objects, because these are all Windows APIs where one side can send some data and the other side can receive the data. Well, WNF lets you do that as well. So if you actually know there's a WNF ID that a process already kind of reads from time to time, if you signal that ID and put a payload, your payload is going to end up in the other process, right? When that process sends a heap address to get the result is basically your data. So you can use this as a way to inject data or code into another process without the standard techniques that everyone on the internet knows about. You can also redirect code execution. Right? Because if you want a process or thread to do something else than what it normally does, typically use an APC or a remote thread, or you change the thread context, or you modify the window long. There's, again, lots of things that hackers and defenders know about. But remember that inside of every process, there's a list of every subscription. And every subscription has a callback and a context. And so basically, if I can find out a WNF ID's callback inside of your process, all I have to do is modify that data structure by passing a different callback. Now I have to worry about control flow guard, signaling the WNF ID, and now that other function runs instead of the real function, and parameter 5 and 6 are the buffer and the buffer size. So by signaling the WNF ID, I now get your process to execute a function it normally wouldn't execute. Now there's a million other things you can do like this, but it's another kind of use case for this. Or you can modify the context. A lot of WNF callbacks, what the callback code does is it gets a context, and then based on that context, there's a V table there, or there's another function pointer there. I could just modify the function pointer in the callback context of a callback, signal WNF ID, the real callback runs, but when it reads its context is different, and something else ends up basically happening. All right, so those are kind of some ideas of things that you can end up doing. To kind of wrap up here, WNF is a very interesting, well-designed kind of feature that was added to Windows 8. Provides lots of useful, legitimate functionality. But because it's highly undocumented and provides almost no visibility, other than a WinBag extension, which doesn't work until Gabby fixed it, you basically have no idea what's really using WNF behind the scenes. And there's really no reason why Microsoft shouldn't just publish the symbols for WNF. It's not like there's some sort of super secret PII mojo in there. They probably just never thought about adding the symbols. That again creates a breeding ground where people can kind of hide. And the last thing here to note is that WNF is basically growing beyond just providing notifications, right? You've got a kernel user mode buffer. You've got things like every edge tab being like sent in WNF. So as more and more things use WNF, well, the question is, like, are people going to start doing silly things like putting code in WNF state names or putting pointers in WNF state names, like one of the ones we found? And so because it can be used to transfer data across boundaries, at Microsoft, they have to be very careful that they make sure that they know, WNF is undocumented. That doesn't mean that it's secure. So definitely, if you're a defender, start fuzzing, start building your own visibility tools, start poking at this, because I'm sure you'll find dragons, and hopefully once we release the tools, that'll give you kind of some more ideas there. All right, and so thank you very, very much. Thank you to Gabrielle for assisting with the talk and helping here. I hope you liked it. And if there's any questions, I think we can move to a different room, and I'll be happy to field those. So thank you very much.